In this video, I'll show how to calculate the value of phi, the golden ratio. I'll start with a particular example. Here's a rectangle with a shape that's very close to the golden proportion. It's 34 units wide and 55 long. Its proportions are measured by finding the ratio of these two lengths. That's 55 divided by 34, which comes to roughly 1.6176. A special property of a golden rectangle is that if you cut off a square from one end, you're left with another golden rectangle. It's smaller, of course, but its proportions are the same as those of the larger rectangle. Let's check this out and see if it's really true. I need to work out the lengths of the sides of this smaller unshaded rectangle. Its longer side is shown here in red, and it's the same as the shorter side of the bigger rectangle. That's 34. And what about its shorter side? Well, I can work this out. Remember that for any square, all the sides are the same length. So if one side is 34, then so is this side. That means that the width of the small rectangle is 55 minus 34, and that's 21 units. As I did with the bigger rectangle, I now need to calculate the ratio of the longer to the shorter side. 34 divided by 21, which comes to roughly 1.6190. If these two rectangles have the same shape, these two proportions should be equal. And you can see that they're pretty close. In fact, the true value of the golden ratio lies between these two numbers. But can I find it exactly? Well, here's how to tackle this question using algebra. To keep things simple, I've called the short side 1 and the long side x. I've already mentioned the special property of the golden rectangle, which is that if you cut off a square from one end, you're left with another golden rectangle. So let me now mark in the lengths of the sides of this smaller, unshaded rectangle. Its longer side is the same as the shorter side of the bigger rectangle, so that's 1. And because the sides of the square are the same, this length must be 1, and that means that the width of the small rectangle is x minus 1. Now here is the key to this. If the two rectangles are in the same proportions, the ratio of the longer side to the shorter side must be the same for both rectangles. Here's this ratio for the larger rectangle, x divided by 1, and here's the ratio for the smaller rectangle, 1 divided by x minus 1. If they do share the same shape, then these two ratios must be equal. This gives us a slightly messy equation, but if I can tidy it up and solve it, I'll come up with a value for x that's equal to phi, the golden ratio. So here's the equation again. X divided by 1 is equal to 1 divided by x minus 1. Let me do some housekeeping to simplify the equation. First, the left-hand side, x divided by 1 is simply x, so I can write it as x equals 1 over x minus 1. Next, I don't like this awkward fraction on the right-hand side, so I'll multiply both sides of the equation by x minus 1. And now the two x minus 1's cancel, and I'm left with x times x minus 1 is equal to 1. I'll multiply out these brackets on the left, x squared minus x equals 1, and finally rearrange the 1 to the other side to get x squared minus x minus 1 equals 0. And if I can solve this equation for x, I've found the numerical value of this mysterious number phi. But how can I solve an equation like this? Well, it has an x squared term, an x term, and a number term, so it's a quadratic equation. And there's a special formula for solving these sorts of equations that involve the letters a, b, and c. A is the number of x squareds, which in this case is 1. B is the number of x's, which here is -1. And the c is the number term, also -1. If you enter these numbers into the formula, you'll find that one of the solutions is 1 plus the square root of 5 all over 2. And if you work that out, you'll get this answer. The decimal string goes on and on, beyond the page, and indeed beyond the known universe, to infinity. And this number is the golden ratio, phi.